Welcome physics students. In today's video we're looking at a Year 10 electricity practice test. Now the format of this test is that I'll present a question, allow you to pause, have a go at it, and then I'll go through the solutions. So let's jump straight into it. The following information is relevant to question 1 and 2. Ben finds an uncoded and unknown resistor. He places it in a circuit to measure the current running through the resistor and the voltage across it for a range of different voltage settings in order to calculate its resistance. Ben collects the following data. So I have here a data table with a range of different voltages and current measurements. So question number 1, plot the data on the graph below and draw a straight line of best fit using a ruler. Okay, so this is pretty simple. First of all, we take our first set of data, 0 volts and 0 amps, and we plot that as a coordinate on our graph. So here's our point 0, 0. We go across next and we've got a current of 1 and a voltage of 4. So a current of 1 meeting with a voltage of 4, we put a dot. A current of 2, a voltage of 8, we put another dot. Current of 3 and a voltage of 12, another dot. A current of 4, a voltage of 16, and finally a current of 5 meets with the voltage of 20 and we make a dot. So most people can plot those, not a problem. And then of course the instruction says to draw a straight line of best fit using a ruler. So we draw that in. 2 marks. Easy. Question number 2. From the graph in question 1, calculate the resistance in ohms of the unknown resistor. Clearly show your calculations. So here's our graph. Now the resistance of this ohmic device is equal to the gradient of the VI graph. The gradient is equal to rise over run. So we're looking at how much has our voltage risen from its lowest point of 0 all the way up to its highest point of 20. So that's a rise of 20 volts. And in terms of a run, how far does it run from left to right? So it starts at 0 amps and runs all the way across to 5 amps. So that's got a run of 5. So the resistance is rise over run, that's 20 divided by 5, gives us a value of 4 ohms. In each of the following circuits, you're asked to calculate the effective or total resistance, RT. Please show your calculations. Remember to use the following formulas. So here's a rule for calculating the total resistance of a series circuit and a rule for calculating the total resistance for a parallel circuit. Each of these questions involve a diagram, and I ask you to pause the video at the end of each question and try it yourself in your books. So question 3.1, calculate the total resistance RT for the following circuit. Pause now and try. Okay, we're asked to find out the total resistance. We know the first resistor. We know the first resistor to be 200 ohms, the second resistor to be 300 ohms, and the third resistor to be 500 ohms. We can see this is a series circuit because current has only one direction to flow. There's no branching. So the equation for the total resistance when it's series is R1 plus R2 plus R3. We substitute our values in, 200 plus 300 plus 500 gives us a total resistance of 1000 ohms. Straightforward single mark question. Question 3.2, calculate the total resistance for the following circuit. And here's our circuit. Pause now, have a look at the answer shortly. This is clearly a parallel circuit. Current leaves the positive terminal of the battery. It reaches this position where it's going to branch or split, also called a node. Some of the current goes to the top, some of the current goes down the bottom. So we're after the total resistance. We know the first resistor has a resistance of 500, and the second resistor has a resistance of 500 also. Here's our equation to work out the total resistance for parallel circuits. Total resistance is 500 ohms to the negative 1 plus 500 to the negative 1 in brackets all to the negative 1. Put that in our calculator and we get a total resistance of 250 ohms. Part 3. Calculate the total resistance for the following circuit. Again, pause and we'll look at the answer shortly. There's 2 sections here. Section 1 I've highlighted in blue, which is clearly a parallel. It's got a 300 ohm and a 100 ohm in parallel. So we want to know what's the total resistance just for that section 1 by itself. First resistor is 300, second resistor is 100. Putting the equation for parallel resistors for just 2 components, and we end up with a total resistance of 75 ohms. So section 1 has a total resistance of 75. Section 2 also is a parallel branch. We can see that quite clearly. We want to work out the total resistance for section 2. The first resistor is equal to 500 ohms. The second is equal to 1500 ohms. Here's our equation. Substitute our values in. Using our calculator, we end up with a total resistance of 375 for section 2. Now clearly we can see that the blue section, section 1, and the red section, section 2, whilst they're both parallel, they're in series with one another. So let's combine these 2 total resistances for section 1 and section 2 in series. So we want to find the overall, this whole combination. Section 1 has a resistance of 75 ohms. Section 2 has a resistance of 375 ohms. Section 1 and 2 are in series, so we simply add them together. So the total resistance for the whole circuit is 75 ohms plus 375 ohms, which gives us a resistance of 450 ohms. Question 3.4. Calculate the total resistance RT for the following circuit. Again, pause, and we'll go through the answers shortly. Section 1 is a 100 and a 400 in parallel, so we want to know the total resistance. First resistance is 100, second resistance is 400. In parallel, so we use the parallel resistance equation, and that gives the total resistance of 80. Now that 80 is in series with the additional 120. So this parallel branch is replaced by an 80, and then it adds on in series with the 120. So the total resistance of those two together will be R1 of 80, R2 of 120. Add them together, we get a total resistance for the whole circuit of 200 ohms. Our final combination circuit, question 3.5. Calculate the total resistance for the following circuit. Pause, and we'll go through the answers shortly. Section 1, we want to know the total resistance for section 1. Its first resistor is 100, as is its second resistor. They're in parallel, put that into the equation, and we get a combined resistance of 50 ohms for section 1. Section 2 down the bottom, we've got a total resistance we're trying to calculate for section 2. R1 is 100, R2 is 100. They're clearly in series. We add them together, so the total resistance for section 2 is 200. We want to combine section 1 and section 2, which are both together in parallel. So the total resistance, we'll be looking at section 1's resistance of 50 ohms and the section 2 resistance of 200 ohms. Add them together in parallel, and we end up with a total combined resistance of 40 ohms. So section 1 and 2 in parallel gives me a total resistance of 40 ohms. So section 1 and 2 in parallel gives me an effective or total resistance of 40 ohms, and then we've got to add to that in series the 100 ohms. So the total resistance of the whole circuit will be 40 ohms plus the additional 100, which gives me a resistance of 140 ohms. The following equation triangles can be used to calculate unknown electrical quantities for questions 4 to 8. So our first triangle, shown on the left, is Q, I, and T, charge, current, and time. Our second triangle in the middle is E, V, and Q, energy, voltage, and charge. And our third triangle on the right-hand side is V, I, and R, voltage, current, and resistance. Question number 4. What amount of charge in coulombs is produced when a current of 20 amps is passed for a time of 10 seconds? Clearly show your calculations. So let's write down the variables that we have from this question. First of all, it says what amount of charge is produced, so Q equals question mark. The current is 20 amps, I equals 20 amps, and T, the time, is 10 seconds. So we only have one triangle that has a Q, I, and T, and it is as follows, and we're after Q. So if we cover Q, we're left with Q equals I times T. Substitute our values in, I was 20, T was 10, in the correct units of amps and seconds, so we multiply them together, we get a charge of 200 coulombs. Straightforward. Question 5. What is the voltage of a battery that gives 40 joules of energy to 8 coulombs of charge? Clearly, show your calculations. So the question states V equals question mark, the voltage is question mark. E, the energy, is 40 joules. And Q, the charge, is 8 coulombs. V, E, and Q, that's our middle triangle. Now after V, so we cover up the V and we're left with E over Q. So V equals E over Q. Let's now substitute and solve. E was 40, Q was 8. 40 divided by 8 gives me 5. So the voltage in this equation is 5 volts. Question number 6. Calculate the unknown voltage drop across the following component. Clearly show your calculations. So here we have a resistance of 4 ohms, a current of 2.5 amps, and an unknown voltage. Let's set this out properly. V equals question mark. R is 4 ohms. I is 2.5 amps. The equation we're using is the VIR triangle, and we're after the voltage. So we cover the voltage up, and we're left with V equals IR. Now we just substitute in our values and solve. I was 2.5 amps, R was 4 ohms, 2.5 times 4 gives me 10 volts. Question 7, calculate the unknown resistance of the following component. And again, clearly show your calculations. So from our diagram, we can see that R is the unknown, the current is 3 amps, and the voltage is 12 volts. Let's write these out. R equals question mark, V equals 12, I equals 3, the current is 3 amps. There's our equation, and we're after the R, the resistance. We cover that over, and we're left with R equals V over I. Substitute our values in. R equals 12 divided by 3, which equals 4 ohms. Question number 8. Calculate the unknown current flowing through the following component. Again, clearly show your calculations. Pause this point and give it a go yourself. We can see the current is question mark, our resistance is 6 ohms, and our voltage is 24 volts. Let's set this out. I equals question mark, the current is unknown. V equals 24 volts. R is 6 ohms, the resistance that is. Our triangle is V equals IR. I is being covered over because that's our unknown, and we're left with V over R. I equals V over R. 24 over 6 gives me a current of 4 amps. Question 9.1. Determine the unknown voltage in the circuits shown below. We're asked to assume that all globes within a given circuit are identical. So first of all, we want to know what is the voltage across this single light globe. Now we can recall the voltage in each branch of the parallel circuit is equal to the supply or battery voltage. So I've got 12 volts coming from the battery, which means this whole branch will get 12 volts. So in branch 1, we have 12 volts. Now there's only one component, one light globe. It will receive that entire 12 volts. So therefore, the voltage across that globe is 12 volts. How about the voltage across this globe in the second branch? So once again, that entire branch gets 12 volts. However, we're only asking for the voltage across this single light globe. So 12 volts across the whole branch. Assuming the light globes are identical, there'll be 50-50 split. 6 to the left, 6 to the right. Each light globe will get equal shares of that 12 volts. So divided by 2 gives me 6 volts per light globe. And finally, a little bit trickier, 9.3. Determine the unknown voltage in the circuit shown below. And again, we're assuming that all the globes within a given circuit are identical. So yet again, the total voltage across this third branch is 12 volts. We're measuring this time the voltage across 2/3 of those light globes. If I'm looking for the voltage drop across 2/3 of the light globes, therefore 2/3 of the resistance in that branch, I know the total voltage to be 12 volts. However, the voltage that I'm measuring will be 2/3 of the 12 are being used up across the two light globes. That will give me 2/3 of 12, 8 volt drop across light globe 1 and 2 in the bottom branch. 10i. Determine the unknown current in the circuit shown below. Assume that all the globes within a given circuit are identical. So this question is asking me to calculate what is this current down the bottom. Recall, the current going into the parallel branch, that is the 9 amps, is equal to the current coming out of the parallel branch. So when it goes into this branch, it splits up. Some goes to the left, some goes to the right, but it recombines back together, which means it will also have 9 amps at the bottom. So current into the branch is 9 amps. That means the current out of the branch will also be 9 amps. Now this time we wish to work out what is the current on the right-hand side of the parallel branch. Let's do a bit of recalling here. The sum of the currents in the two parallel branches must equal the current going into the parallel branch. So if we start with 9 amps, it must split up. It might be 8 in one and 1 in the other to add up to 9. It might be 2 in one and 7 in the other. It could be 6 in one and 3 in the other. It could be 4.5 and 4.5. It must add up to 9 amps in total. So our second point on our recall, the current running through each branch depends upon the resistance of the individual branch. Branch 1 has double the resistance of branch 2. Accordingly, it will only get half the current to that of branch 2. So there's going to be a 2-to-1 ratio of current here. Twice as much current will go through branch 2 because it only has half the resistance of branch 1. So the resistance in branch 1 will equal double that of branch 2. Therefore, the current in branch 2 will be twice that of the current in branch 1. Now we're going to find a ratio of currents that will split up to equal 9. That's a 2-to-1 ratio. So the current coming from the supply, which is 9 amps, must equal the current through branch 1 plus the current through branch 2. It has to be accounted for. So the only way you can get a 2-to-1 ratio that adds up to 9 amps is if we have 3 amps going in branch 1 and 6 amps going through branch 2. That's a 2-to-1 ratio that adds up to 9. So in this scenario, current for the unknown symbol I must be equal to 6 amps. Probably the trickiest question on the paper. 10.3, determine the unknown current in the circuit shown below. Once again, we're assuming that all the globes within a given circuit are identical. We just discussed this scenario. We know the supply current coming from the battery was 9 amps. We're looking to work out what is the current in branch 1. And from our previous question, we worked out the current in branch 2 was 6 amps. The supply current must split up. Some of it will go into branch 1 and some will go into branch 2. So if I've got 9 amps coming from the battery, 6 of it going into branch 2 on the right hand side, that will leave me with 3 amps going through branch 1 on the left hand side. So the unknown I current in this diagram will be 3 amps. Question 11.1. State the current measured by the following ammeter displays. Be sure to state the correct unit of measurement, that is either amps or milliamps. So we have here the 50 milliamp scale being chosen and the needle going across up here. So let's go through this methodically. First of all, if we're looking at the 50 milliamps, that means our full scale deflection is 50 milliamps. Therefore, we're using this middle scale. Again, the 50 milliamps, and we look on our right-hand side where the needle would be fully deflected, what we call full scale deflection. 50 is on the middle scale. So our needle on the middle scale is somewhere between 0 and 10. Those 10 milliamps are divided into 1, 2, 3, 4, 5 smaller sections. 10 divided by 5 gives me a small division is equal to 2 milliamps. So we can now count across. That'd be 2, 4, 6, 8 milliamps. So the reading on this scale will be 8 milliamps. We know it goes up to 50 in that middle scale, but remember, of course, it's being measured in milliamps. So that represents 8 milliamps. 11.2, let's do this again. This time we're looking at the 500 milliamp scale. So the 500 milliamp scale on the full scale deflection, that is the right-hand side, is the top scale, which means our measurement is between 200 and 300, and needle is between 200 and 300 on the top. And we know that between 200 and 300, that represents 100 milliamps. And there's 5 little divisions between those on our scale. So 100 milliamps divided by 5 individual divisions means each small division is worth 20 milliamps. So this would be 220 milliamps. That's our reading. Our final one, 11.3. Yet again, we want to state the current measured by the following ammeter display. We're now on the 5 amp scale. So that represents on the full scale deflection, right around on the right, 5 is the bottom. So we're measuring on the bottom scale. So this needle is between the 4 and 5 amp. That represents a difference of 1 amp and there's 5 divisions. So each one of these small divisions, 1 divided by 5, will be equal to 0.2 of an amp. So this particular needle is measuring 4.2, 4.4. This would be 4.4 amps. Question 12 is to do with color coding. What we've got to do is use our color coding table and fill in the gaps on our table that we've got here below. All these squares are empty, we need to fill them in. Have a go at this and we'll come back in a second and go through the answers. Okay, let's have a look. Our first digit in our unknown row is a 1. Now a 1 for first digit is represented by brown, so we write in the word brown, correct. Our second example has a second digit of 6. A digit of 6 represents a color of blue, so we write in the word blue. Our third example has 1, 2 zeros after the first 2 digits. So you've got digit 1, digit 2, that's the first 2 colors of orange and white. And then you've got 2 zeros, which is the same as a multiplier of 10 to the 2, which represents the third color band of red. Example number 4, we had to calculate the color of the fourth band. The fourth band gives us the tolerance. We're told it's plus or minus 5%. Plus or minus 5% is the color gold, so gold is entered in. Our fifth example takes into consideration the first 3 bands. So we've got a red. Red represents the number 2, so we put 2 in. We have a green. Green represents the second digit of 5, so the 5 goes in. And blue is our multiplier. The third band is our multiplier. So blue represents 10 to the 6, effectively like a million. And a quick way of writing that down is mega. Mega means 10 to the 6. So our correct answer here will be 25 mega ohms. Our final example. This one required the tolerance to be copied into our table. The color we have is gold. Gold represents a tolerance of plus or minus 5%. Simple task. Sam collects a resistor with the following band codes. We have a green band, a red band, a brown band, and a silver band. Question 13.1. What does the coding predict the resistance of the resistor to be? Give that a go. So using our table, the first band is green. That gives me a digit of 5. Second band is red. That gives me a second digit of 2. The third band is brown. That represents not a digit, but the multiplier. It means multiply by 10 to the 1 or multiply by 10. So I've got a 5, 2, and I put in 1, 0. That 1, if you like, represents the number of zeros we're adding. Finally, the silver, the fourth band, is the tolerance. So from our table, we see that silver is plus or minus 10%. So what does the coding predict the resistance of the resistor to be? It predicts it to be 520 ohms plus or minus 10%. Part 2, what does the coding predict the maximum value of the resistor to be? So previously we discovered the resistance was 520 ohms plus or minus 10%. So its maximum value will be the plus 10%. So we're starting at 520 ohms, we're going to add on 10%. Now a quick way of doing this, when we're adding 10%, is simply multiply the value by 1.10. Multiplying by 1 will return the same answer. The 0.1 will add on an extra 10%. So 520 times 1.10 on our calculator gives us a maximum value of 572 ohms. Part 3, what does the coding predict the minimum value of the resistor to be? Please give this one a go, pause and come to the answer in a second. So we start with 520 ohms and we're going to take away 10% to find our minimum value. Now, when we take away 10%, that's the same as multiplying our existing value by 0.9. If we were to multiply a value by 1, that will return the same value. If we're multiplying by 0.9, that is 0.1 less than the perfect 1. That's being reduced by 10%. So using our calculator, 520 ohms multiplied by 0.90, which is a 10% reduction, gives me the smallest possible value of 468 ohms. Question 14. Determine the unknown quantities, shown in red, in the series circuit shown below. Clearly show your calculations. So first of all, recall, the current remains the same everywhere in a series circuit. So when the current leaves the positive terminal of the battery and moves all the way through the circuit, its current remains exactly the same. So the current at the top here of our circuit will be the same as our 1 amp down the bottom. So the unknown value for I is 1 amp. Let's look for some more unknown values. Examine the 8 ohm resistor. So I've got that highlighted in green. We're asked to work out what is the voltage across the 8 ohm resistor. We know the resistance is 8 ohms. And we also just stated that the current is 1 amp everywhere in the circuit. So that means there will be 1 amp flowing through the 8 ohm resistor. We've got our R on I and we want to find the V. Let's use our Ohm's law triangle. V is our unknown, so we cover it and we're left with V equals IR. Let's substitute in our values specific to this 8 ohm resistor. The current flowing through it is 1 amp and the resistance we know to be 8 ohms. V equals I times R. That gives me a voltage of 8 volts. So the voltage V1 is 8 volts. Next, let's examine the second resistor. Now recall, the sum of the voltage drops in a series circuit is equal to the supply voltage. So we started with 12 volts, and we just calculated that we're using up 8 volts across this first resistor. That will leave us with only 4 volts remaining for the second resistor. This is a very simple calculation. And there's a way in which we can express it. The supply voltage is equal to the voltage drop 1 plus voltage drop 2. There's only 2 resistors in this circuit. So we start with 12 volts. 8 volts we just calculated in the previous question is found or dropped across V1, and the remainder is left for V2. So V2 is the difference, which comes out to 4 volts. Now, we've only got R2 remaining to work out as an unknown quantity. So let's look at R2, our second resistor. The resistance is question mark. We just determined there's 4 volts across R2, and as we just stated earlier, we know the current is 1 amp all the way around this circuit, including through the resistor R2. Ohm's law, VIR, we want to find the resistance. We cover it over. That leaves us with an equation, R equals V over I. Voltage is 4 across this resistor. Current is 1 through this resistor. Divide 4 by 1, we end up with a resistance of 4 ohms. So the second resistor has a value of 4 ohms. Calculating these unknown quantities is as simple as understanding series circuits, what happens to the voltage within a series circuit, and what happens to the current within a series circuit, and then being able to apply Ohm's law to specific components. Our final question, question 15. Determine the unknown quantities, again shown in red, in the parallel circuit shown below, and you're asked to clearly show your calculations. This question is worth 6 marks because there's 1, 2, 3, 4, 5, 6 unknowns shown in red. Have you got these questions? Then check out these solutions. Recall, the current going into a parallel branch must equal the current going out of a parallel branch. So this current A coming into the branch, it gets split to the left, to the right, and then it combines and continues on back to the battery. So the current going into the branch must be equal to the current coming out of the branch. Therefore, current IA must be equal to 3 amps. Another simple point to start here is to recall that the voltage across each parallel branch is equal to the supply voltage. So that means the voltage across the first branch will be equal to 12 volts, and the voltage across this second branch will also be equal to 12 volts. Let's now look at the 6 ohm resistor that I've highlighted green. Let's write down what we know. We're asked to find the current. What is current 1 traveling through this 6 ohm resistor? We know that that single resistor has a resistance of 6 ohms, and we just stated the voltage across this single resistor is 12 volts. This branch has the same voltage as the battery, and all of it is found across this single resistor. So I want to find the I have the R, I have the V. Ohm's law, V equals IR. I want to find the current, so I cover that with my hand, and I'm left with I equals V over R. Let's now substitute and solve. V was 12, R was 6, 12 divided by 6 gives me a current of 2 amps. So the current going through the left-hand side branch of this parallel circuit is equal to 2 amps. Let's now look at the right-hand side, the second resistor. Now we mentioned before the sum of the current through each branch must equal the supply current. We worked out there was 3 amps at the top as there's 3 amps at the bottom. So 3 amps comes along, and we just determined that 2 amps flows through the left of this branch. What must be left of the 3 amps that flows through the right? That's pretty logical. So the current coming from the battery, the supply current, the symbol IS, must equal the sum of the current in the first branch, I1, plus the current in the second branch, I2. So we have 3 coming in. We just determined there's 2 amps going to the left in the first branch. Clearly that means there must be 1 amp remaining in the right branch, in branch 2. Let's look at our final calculation. We want to work out what is the resistance R2. So R is equal to question mark. The voltage across this second branch is 12 volts, and we just determined the current through the second branch to be 1 amp. We can use our triangle V equals IR. This time R is our unknown, so we cover it. And that gives us R equals V over I. For this particular branch and this component R2, we've got a voltage of 12 and a current of 1. Divide that through, that gives us a resistance of 12 ohms. So our final calculation for this particular practice test was the second resistor R2 was equal to 12 ohms. I hope these examples have been useful in preparing you for our upcoming topic tests. If you've got any difficulties on these questions, go back and review them. Study hard and do well. You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.